This is the sun. Over the next 8 billion years, it's going to grow and grow and grow and eventually consume the Earth. Tiny little changes will all add up and eventually destroy the entire planet that we call home. Little changes can have a really big impact over time. But there's enough scary stuff going on right now, so how about we just chill for a little bit and talk about code? Hi, I'm Craig, and much like the sun, I'm a super hot giant ball of existential terror. Over my career, I've worked on a number of reasonably large and old code bases. I've worked in places that push the ideals of Agile, aiming for incremental change and always shipping working software. But despite that, I've been involved multiple times in big confrontational UI changes where there was no real going back. Incremental change is hard. Legacy software is also hard. Codebases evolve over time, and a mature system is a very powerful thing. You really shouldn't underestimate the value of working software or having a known system with real users. Billion-dollar companies often exist on top of old code built up over years. And systems like this are quite stable until you try to change them. There comes a point where it's not actually stability, but rather a gradual decay. You have to ask what the system might look like in 6 months or 6 years. You can end up in a state where the codebase cannot be safely changed without making something worse. You've optimized for a current paradigm and reached a local maximum. A coworker once referred to our codebase as being in a state of accidental immutability. No matter what we did, something broke. There wasn't a safe path from where we were to where we wanted to be. Most of us have some ideas of what we might like our codebase to be like, but that might seem out of reach entirely. Your current codebase is what it is, and you've got to keep shipping, so changes have to happen, and they happen dangerously. Everyone wants something to be better, and eventually maybe someone says, why don't we rewrite the whole thing? And rewrites are exciting. It's kind of like a revolution. You can move fast and break everyone's stuff and build newer, better, shinier things. And sometimes revolutions are necessary. Sometimes a system is so broken that the best path through is to burn it all down and start again. But they can also be dangerous, and a lot of people can get caught up in the middle of you tearing everything apart. With software, there are many cautionary tales of revolutionary change where it's all gone wrong. In my experience, it inevitably involves scope creep and too many things changing at once. You may end up through the other side, but there's always a cost. If you're not careful, precious institutional knowledge can be lost. So, are there options other than a burn it all down revolution? Maybe you can make things better within the existing codebase. You might make a new branch and start working away at some improvement. This works for small changes, but what about large bits of technical debt? It's often hard to prioritize this kind of work and hard to do it all at once, so trying to do a little bit at a time is a great idea. But that means that the branch could live for a long time, and merging it gets harder and harder. Along with the technical challenge of keeping the branch up to date, you've also introduced a communication problem, because other contributors continue doing things the old way. Maybe to communicate the plan to the team, you decide to try to add a lint rule. But there are hundreds of errors, so you just disable the rule in all the places that it currently fails. Or maybe just make it a warning, and then everyone ignores it. People continue to do things in the old way, and the decay continues. Sometimes it's possible to completely automate a change, which can reduce the pain of that communication breakdown. Some things can't be automated completely, but often you can get 90% of the way with automation, and then tidy up manually. But of course, there are a large number of problems that can't be automated. Humans are currently still the winners when it comes to more creative or subjective things, which is often the case where there is code involved. So how do we break down these kind of problems into something that can be dealt with more easily? An evolutionary algorithm is an algorithm that explores possible solutions using a heuristic that is inspired by natural evolution. These algorithms reflect the process of natural selection, where the fittest individuals in a population are most likely to successfully reproduce, to produce offspring of the next generation. Each generation is slightly better than the previous, an incremental improvement towards some better future state. One specific type of evolutionary algorithm is called a genetic algorithm. And there are two key inputs into a genetic algorithm. The first input is a genetic representation of solutions to the problem. Each variable in the solution is called a gene, and all the genes are combined into a chromosome, which represents one solution to the problem. A number of potential solutions are collected together as a population. To solve a problem with a genetic algorithm, the implementer has to first break a problem down into all the individual elements that might impact the solution in order to determine what each gene should be. The second input is a fitness function, which takes a chromosome from the population as an input and evaluates the fitness score of the solution. Each chromosome in the population is evaluated by the fitness function, so that each chromosome has a fitness score. Once the fitness of the whole population has been evaluated, the selection phase begins. First, solutions are sorted by their fitness scores, and low-scoring solutions are removed from the population. Then, pairs of chromosomes reproduce until the population is back to its original size. Finally, some small number of genes within the new population are mutated to introduce some randomness into the mix. Then the new population is scored, and then the next round of selection happens. This continues for many generations, and the population tends towards some better state. Ultimately, it comes down to the fact that humans are pretty good at breaking down problems. If you break a big problem down into a set of smaller problems, they can be easier to solve individually. Wouldn't it be great to have a way to describe a change you want to make in your codebase and define what incremental progress towards that final state looks like? We need a way to break down the difference between the current state and some future state into smaller pieces that can be dealt with incrementally. We need a way to break down our codebase into countable bits of data. But that's nothing new, right? It's a slightly different way of thinking about it, but that's what TypeScript or ESLint or Jest or any other number of tools already do. They take our codebase and transform them into some number of errors or warnings or something countable. We can think of these tools as our fitness functions. What we need is a way to compare the quantified state of the codebase between 2 points in time. We can run some fitness function over the main branch of the codebase to get a representation of the current state. We can run the fitness function again on some new branch to get the fitness of the new state. What we need is to define a comparison function to assess the difference between the two states. A comparison function has a job of working out if the new state is better than the old state, worse than the old state, or the same. The comparison function acts as a constraint, guiding your codebase in the right direction towards being better. But we can't change branches all the time to evaluate the fitness, so is there a better way to keep track of the current state of the main branch? It's become pretty common to store auxiliary information about a codebase in the repository. Chances are that somewhere in your codebase you've got a dependency lock file or a Jest snapshot file. We can use the same idea and store the current quantified state of the code in the code. And with that, we have the three little pieces we need to enable gradual incremental migration. We need a fitness function that takes our codebase and turns it into a quantified state of the codebase. We need a comparison function that takes these two quantified states and determines if one is better than the other, worse than the other, or the same. And we need a mechanism for writing the results to disk so they can be stored in source control and compared between branches, kind of like a Jest snapshot file. I've been working on wrapping this idea up in a little tool. I've been calling it Betterer. Betterer is a tool designed to make incremental improvement easier. You can think of Betterer as a test runner like Jest or Mocha. The difference is that a Betterer test starts out as broken by default. A Betterer test is a way to communicate to other developers that there is something you want to improve in a codebase, without the need for burning everything down and starting again. You can check out the docs online. Let's have a look at how it works. We can initialize Betterer with npx betterer init to get Betterer set up in a codebase. When we run the initialization script, it updates the package JSON with a new script to run Betterer and adds a new dependency on the latest version. The initialization script also creates a brand new Betterer config file, which is the entry point to your tests. Straight out of the box, that's enough for Betterer to start doing its thing. Of course, right now it does nothing, since we haven't defined any tests. So let's fix that. So what should a test do? The test is a fitness function for our codebase, and it can be basically anything you want, as long as you can represent the result in a way that can be compared. I have a project that I want to convert from JavaScript to TypeScript, so let's write a test that counts the number of JavaScript files in a codebase. We define a new test in the betterer.ts file and import betterer test from betterer. We're going to call our test migrate.js to ts. Next, we need to write our test function. This is the function that scores the fitness of the codebase. For now, we're simply going to use the glob library to count up the number of files with the JS extension. A number is nice and easy to compare, so that's good. Next, we need our constraint function, which does the comparison between test results. In this case, we want our test to be better if the new result is smaller than the expected result. In other words, if we have fewer JS files, the test got better. To compare smaller numbers like this, we can just import smaller from betterer constraints. Now if we run betterer again, we're going to see something more interesting. Our test got checked for the first time. So what did this do since we had nothing to compare it against? Since we didn't have an existing result to compare, betterer just runs the test and takes what it gets as the base state. It serializes the result and stores it in a new file called betterer results. In this case, there are 9 JavaScript files in the codebase. If we run betterer again, we will see that our result is the same. We didn't change anything in our codebase, but betterer found the results file and uses that as a comparison point. This is fine. Nothing got worse, so we haven't gone backwards. So along comes our friendly neighborhood engineering manager, and they're adding a new feature, and they haven't heard about our new plan to migrate to TypeScript. They add a new JavaScript file to the project, and when they try to commit, they get a big error, and they can't move forward. That's good for the state of our codebase, but maybe it doesn't quite communicate what's going on as well as it could. We can make it a bit more clear by using a betterer file test. The way you create a betterer file test is a bit different. It just takes a function with 2 parameters, file paths and file test result. In this case, file paths will be a list of all the files that match the include glob. The file test result is an object that we will use to tell betterer about issues. The body of the test is pretty simple. Since the test only targets JavaScript files, we just need to create an issue for each file passed to the test. We read the contents of the file and then call add file on the file test result. We then call add issue on the file, pass 0 and 1 to attach the issue to the first character of the file, along with a helpful error message. If we run it again, it should be much better. Now there's much more detail about what went wrong. Because we used a betterer file test, there are still 9 files found with issues, but there is a lot more detail in the results file. With the results file updated, we can commit and merge our updated test, and our engineering manager can update his branch with the updated test. Now, because our engineering manager only gets about 15 minutes to code each week, they don't have time to fix the JavaScript right now. But that's okay. They can use the update flag to force betterer to update the results file, just like with a Jest snapshot. This means they can move forward and make a pull request. Sometimes you have to make things a bit worse so you can continue to move forward. Using update forces betterer to update the results file, and now we can see that we have 10 total issues. Now the results file matches the state of the codebase, so betterer will go back to reporting that the test is the same, and we're back to a stable condition. Next, someone on the team comes along and they migrate the new file that the engineering manager added, as well as 1 other JavaScript file. They run betterer again, and it reports that 2 issues were fixed. Now we're even better than we were before. Since things got better, betterer will overwrite the results file, locking in the better state of the codebase. We can apply this idea to a lot of things. We could write a test for enabling scripted TypeScript compilation, or use ESLint or stylelint to introduce new lint rules. We could track to-do comments with a regex matcher, or we could even lint other languages like Kotlin or Swift. We could enable strict template type checking for Angular, or check Axe violations, or even code coverage with Jest. There are many possibilities. Betterer comes with a few tests that are built in, which can help you get started. So that's Betterer. I've been working on it for more than a year now, and I'm still super excited by this idea. If this is interesting to you as well, please reach out. We're probably not going to stop the Earth being swallowed by the sun, but we might be able to make some stuff a little bit better. Thanks so much.